We are ready to restart. Do you hear me? Good, thank you. So this is, as an approximation, what TCP Reno, this version of TCP, does to the internet distribution of rates. So it uses a utility function that is given by this formula. So this formula is if we count everything in packets. So the rate xi is in packets here. And you see that the tau I, which is the round trip time, plays a role. What does this imply? This is what we will now discuss. Well, the utility depends on the round trip time, and the question is, how does the utility depend on the round trip time? So if two sources have different round trip times, they will have different utility functions. If the utility of a function of a source A is smaller than the utility of a source B for the same rate, if their utility functions of A are smaller, that means that the network will try in its allocation, will try to give less to source A because the utility of this is smaller. So if I want to maximize the total utility, I will give more rates to those that provide more utility. I mean, think of utility as money. The problem is the same as if somebody would receive money proportional to the utility. By giving a rate xi to every source, you will give more to those who give more money to you. That is what the utility function logic means. So we need to understand how the utility depends on the round trip time here. Now it's a combination of two factors, 1 over tau, so it decreases the round trip time. Then there's tau here, which is increasing, but the arctangent is a strongly concave function. It's growing much more slowly than a linear function. So the combined effects means that it's decreasing. To illustrate this, I'm plotting this function for a given x. Now, as a function of tau, we see that when tau increases, the utility decreases here. What does this imply? Well, let's test the implication on a simple example here. Here I'm assuming I have a bottleneck link with two sources that are trying to access a destination via this bottleneck link. I'm assuming this is the only constraints that we have. So the sources and the destination are very fast. The only limitation is this link here. I'm ignoring the return path. But for some reason, the round trip times are not the same. The round trip times are given here. For S1, it's 20 milliseconds. For S2, it's much larger. Why could that occur? Well, perhaps S2 is connected via an access network that is very high performance, but has a large delay to this router here. What will happen if both are trying to use TCP Reno to get to dictate the share that they will obtain from the network? I close the poll in a few seconds. And the majority says A, which is the correct answer, because of the bias that we said in the previous formula. The utility is less when the RTT is large. Therefore, TCP tries less hard to give a high rate to sources with large RTT. S2 will get less. So if we do an experiment here, where we plot as a function of time the bytes that were acknowledged by the source, that's something that we can easily plot with a TCP. There are tools, easy tools to do this. So that gives us the total amount of data that has been received. So the rate being the slope here. We see that roughly speaking, S1 gets twice as much as S2, right? So that's exactly what happens with TCP. In fact, with practically all versions of TCP, we have something similar that happens. If you have a large round trip time, even if you're fighting for the same resources, the fact that you have a larger round trip time means that you will receive less here. This is called the bias of TCP against large RTTs. This is something that is often misunderstood when you read blogs or user manuals of things. Usually people who didn't take the time to read a few chapters of congestion control misunderstand things. So let's see what the reality is. Two sources that have different RTTs are not treated equally. The source with the larger RTT obtains less, right? Now, there are two aspects to that. In a network where we've seen examples illustrating the proportional fairness, where we had one flow that was using all the resources of the network, and the other flows were each using only one resource. And we saw that proportional fairness would give more to the sources that are using only one link compared to the source that is using a large number of links. Now, of course, there is a correlation between the number of links, the number of hops that a TCP connection has, and its RTT. It's positively correlated. If you go far, if you use many hops, you'll have a larger RTT. Not always, but very often that will happen. So in that sense, this bias against large RTT can be confused with a proportional fairness mechanism, which will occur with TCP because we see that TCP uses a utility function that's close to the logarithm, so it's close to proportional fairness. However, so it's a desirable bias in a sense, and it's simply the theory of proportional fairness. You're using more hops, you get less than somebody who's using fewer hops. Will still make sure you get something, but you're using a larger part of the network. If you use multiple parts that are each congested, then you get less. That's not a problem. It's part of the proportional fairness theory. However, the simple fact that the RTT is large in itself introduces a bias. We can interpret this. The cause is that we do additive increase of 1 per RTT, or approximation of it. Now, 1 packet per RTT means the rate that we increase is MSS over RTT. If RTT is large, the rate increase is small, right? And also, we do that less frequently. So the increase is less frequent and is by a smaller amount in number of rates. So if you have a larger RTT, then you are using additive increase, multiplicative decrease approximately, but with an increase term that's less large than others. So you're competing with a disadvantage, with a handicap here. So there are those two parts in the bias. One part is an emerging property that comes from the utility function. Another part is a bug, in fact. It's a bug of TCP Reno. TCP Reno should correct this. It's possible to do that, but it has never been done, and it will probably never be done in this form here. Which means that this bias exists, and this is a second reason for content distribution network. So a bug gives an opportunity for startups to create businesses. If you want to download a lot of content from California, even if you have multi-gigabit per second between here and California, you will not have a very good throughput because your RTT will be large simply by the propagation of lights. You will have 100 millisecond round trip time if the network is excellent. You'll be competing with people in California who have perhaps 10 millisecond. You will get 10 times less, roughly speaking. So you have to push content close to where people are because of this bug in TCP congestion control. There are other reasons, of course. There is also the proportional fairness thing. If you need to go a very long way to get somewhere, you might fight for many resources, and that gives a less predictable performance. Analyzing the performance of TCP is important for a number of things. We'll see, for example, a use of the TFRC protocol, TCP-friendly UDP applications, but also in general to understand how you should dimension your network, should you deploy content distribution network for this content, etc. And there is a simple formula, which is also explained in the lecture notes. So if we go beyond the analysis that we did in terms of utility fairness, we can see that the utility fairness thing allows us to cast the problem of computing the rate that a TCP connection will get as an optimization problem, which is doable in theory. In practice, that's not what we have. In practice, we observe only parts of the network, and what we can observe is the loss. The loss is given by a parameter Q, which is the fraction of packets that is lost, or marked with congestion. We will see in a few more minutes that there's an alternative to the losses here. Right now, this is losses here. So if a given connection gets a certain fraction of packets that are lost, then the mechanics of additive increase, multiplicative decrease will lead to this formula here. So TCP will get approximately this. This formula says that the throughput, the useful amount of data counted by counting only the content of the TCP packet, is equal to the maximum segment size. So this is a theoretical formula assuming all packets are equal size, multiplied by a constant, divided by the round trip time, divided by square root of the loss probability here. So this is a very crude formula, like all the modeling that's done in this domain. It assumes that losses are rare and that the slow start and fast recovery, the impact of that can be ignored here, which is true when losses are reasonably rare here. If losses are catastrophic, if you start with slow start, then you have a loss, you do slow start again, and you spend a lot of start in slow start, this will not be true. There are other formulas for those things. They are equally approximate, but they are less approximate when there are many losses, for example. But we'll stay with this formula because it explains quasi everything. In particular, you see the dependency on the round trip time is very significant here. For example, if we continue the example we saw a few minutes ago, and I ask, will S1 or S2 get more? Can we quantify exactly the difference in throughput? Or is it impossible? Did not work. Do you see a poll on Speak Up? No. Okay. Which is consistent with the fact that I've lost connection here. Second try. I close the poll in a few seconds. And the correct answer is the majority vote, C, because we will see that if the router is fair, which is probably the case, unless you do something specific, the probability that a packet is lost by the router here due to congestion will be the same for the two flows. So the two flows which have a single bottleneck here will perceive the same queue. And then the loss throughput formula says that if the queue is the same, then the throughput is inversely proportional to the round trip time. So the proportion is 3. So the sorry, what is 7/3? Why is the proportional inversely proportional? So it should be, the round trip times are 20 plus 10, 30 and 70. So it should be inversely proportional to 7 and 3, which gives this ratio here. So roughly speaking, double. S2 will get, roughly speaking, double. So this is how things are in the internet. There is a bias, but we can also quantify the impact of this bias. It's roughly speaking proportional to the round trip time. Voilà, what we've seen is TCP Reno, which is the historic version of TCP congestion control, plus the other parts of TCP that we've discussed before, and is still the basis for most implementations of congestion control, with one big exception, which is TCP Cubic, which is a more recent variant of this. There has been many variants of TCP congestion control. Finding a new version of congestion control has been for some time the favorite topic of SIGCOMM papers. And so there's been TCP VGAS. Recently, there's been TCP BBR. Those two don't really work. They've been deployed, they've been tried. There's been papers that say that they have severe problems. So there's a huge number of them. And we will, of course, not go through all of them. But TCP Reno and TCP Cubic are the two forms of congestion control that are really surviving this evolution race. TCP Cubic is addressing some of the shortcomings of TCP Reno. Right? So what are possible shortcomings of TCP Reno? Well, let me try to mention a few. Well, there's the RTT bias. We've seen it's not nice if you're at the other end of the world. There are other problems. Periodic losses must occur. That's the only way you know when you need to stop increasing, right? So when there is a loss, then it's not so nice. TCP will have the window stops sliding. Also, if you have video applications, you lose a packet, the application needs to do something about it. So it's not so nice. Second, we go via the window. So large bursts are possible, which means that the burst, even if we think we control the rate, we do that only over the long term. So bursts are what dictates losses when the buffers are not too large. There's also what is called self-inflicted delay that we will discuss a bit more later. But there is another issue which occurred when people did things like, for example, huge backups in data center over remote locations. So assume, for example, you want to transfer one big file. So doing the kind of programs you did in lab 3, you open one TCP connection and you say, read this file, copy it to another machine. Now, if your file is huge, this is what will happen. And if your performance is very large, so I'm assuming I'm over a network that allows me to give me multiple gigabits per second for one single TCP connection. Of course, this is very atypical when we are, you and me, when we're over the internet like we are now, we don't get gigabits per second for one TCP connection. Zoom is using a few TCP connections. We probably use a few megabits per second, not gigabits per second here. But when you do a massive backup, for example, or a replication of a data center to a remote location, or you're synchronizing databases, or when you're doing experiments at CERN where you have bombarded particles and you get petabytes of data that you need to analyze and transfer from one disk farm to another, you get that type of bit rate here. Now this is what TCP will do. TCP will start in slow. So assuming I have a capacity of 10 gigabit per second, then, and I have only one TCP connection. So TCP will very quickly go to that until it hits the capacity, slow down, decrease the window by 2. There will be perhaps fast recovery, a few details that I'm skipping here, and then will increase again with additive increase, etc. Now the thing is, when we are with such large numbers, the additive increase here takes a very long time. It takes order of an hour to get from 5 gigabit per second to 10 gigabit per second here, which is what was no big deal in the other figures I showed before, because everything was fast. We were oscillating, plus there were many connections, so things were in a moving target. But here I have only one big pipe that I would like to use. If I do this, then these oscillations have a cost. In fact, in average, if we do, I'm oscillating between 5 gigabit and 10 gigabit. In average, we can see that we get only 7.5 gigabit per second, not 10. So we're wasting 25% of the capacity. So that is the problem of the brutal decrease by 50%. We will see that there are two methods to avoid this. The first one is the method of Cubic here. The other one is the method of DC TCP that we'll see a bit later there. So this is the problem that we want to solve in this example. One solution is TCP Cubic, which is the standard version of TCP in Linux. So to play with TCP Reno alone, we will see in lab 5 how to do the configuration to get there. So TCP Cubic does the following change. So it uses everything that we've seen before. It uses additive increase, multiplicative decrease, slow start, fast recovery, all this, with one exception. The only thing is the phase called congestion avoidance, which is when we do the additive increase, is replaced by this blue curve here. The red curve here is showing how the window increases when we receive no negative feedback with the classical formula of Reno, for example. Cubic says, well, we will do something different, which is given by this blue function here. This blue function is in fact a cubic function. It's x to the power cube, rescaled at some value centered around some value, k here, where k is chosen as the time 07 W max. So W max is the window, the value of the congestion window when the loss is detected, which is when we start this phase here. When a loss is detected, if we ignore the details of fast recovery or slow start, we decrease by 50% with TCP Reno, and we increase linearly. Here we will decrease by 70%, and we will increase by this function here, which is a cubic function designed in such a way that at some point here, it will reach the value of W max here. And then if this value of W max was the correct value, we had a loss, but this is, for example, a loss due to congestion, not due to congestion, or it's an accidental loss, then we will get back there, and that's the end of the story. It's good. If we need to increase, which is what would happen in the motivating example I gave a few minutes ago, we'll first start very slowly because the cubic function given here is very slow at the beginning. And then it will become very fast, faster than a quadratic function, a cubic function here. So when we pass this value here, we go very, very fast here. So this is what cubic is doing. This is why it's called cubic, because this function is cubic here. Now there's a catch here. The function I gave before was with an RTT of 100 milliseconds. If we change the RTT, if we make it smaller or larger, then we have a radically different thing here. So cubic increases the window in a concave way here. This is a concave frame. So in something that is increasing less than linear here, until it reached W max, then increase in a convex way very fast here. However, when the RTT is large here, so it works well when the RTT is large, cubic will increase faster, but when it is when the RTT is small, then it will be increasing slower here. So cubic wants to avoid this, so it wants to be faster, so it will make sure it's at least as fast as additive increase. So it will compute the window that it would get with additive increase and will take the best of the two here. Now, while doing that, there's a small complexity here, which is that cubic does a multiplicative decrease by a factor of 0.7 here. So the beta, which for Reno is 0.5, is 0.7 here. So when we compute this additive increase multiplicative decrease, we compensate for this increase, which is smaller, by the decrease, which is smaller, by an increase, which is also smaller. So additive increase will increase by a fixed amount, r cubic, which is smaller, is in fact 50%, roughly speaking, of what Reno would do. So we decrease less and we increase less, such that if we would be doing exactly additive increase multiplicative decrease, we would get exactly the same. Of course, cubic wants to get more, so by this trick here, it will be sure that it gets at least that much. It will always get the same as Reno or more. If we did not do this thing, it might be that this would be an unfair comparison. With a bit more work, we can obtain the equivalent of the loss throughput formula for cubic, which is saying that it's obtained by the max of two terms. A first term, which is exactly the TCP Reno formula, and this thing here, which is coming from cubic. So we see that, because again, cubic wants to get at least exactly as much as TCP Reno would get, and in some cases it will get more. When will it get more? Well, it's hard to see. It will get more when the blue formula here is larger than the red, which is hard to get in linear scale, but in log scale it gives straight line. Here I'm plotting as a function of the loss probability Q, and the RTT gives different lines. I'm giving the throughputs that those two formulas give. The blue lines are the blue formula, the red lines are the red formula, and cubic will get the most of the two. So cubic will be this greenish line here, which depends on the RTT. There is still a dependence on the RTT. When the RTT is 100 millisecond, for example, this is the loss throughput formula of cubic. When the loss probability decreases, which means when the network is less and less congested, the rate of cubic increases. But this, you see here, this is a logarithmic scale, so it increases, of course, much faster here. So the take-home message, the TCP Cubic connection gets more throughput than TCP Reno. When? Well, when we are in this region here on the left, which means when the loss probability is small, which means when the bandwidth is large, or also when the RTT is small here, which is a bit complicated to analyze, but this is what happens in reality. See that there is still a dependence on RTT, in particular when we are in the region, the desired region where cubic makes a change, which is when cubic gives you a very, very large throughput. Then the dependency, the bias against RTT, which still exists, but is much smaller, because it's now at a power 0.25 instead of a power 1 in the denominator. Voilà, so this is what cubic does. Again, to get a very large throughput with Cubic, to make a difference between Reno and Cubic, you need to be in this region where the throughput is very, very large here. So when we are reaching the gigabits per second with small RTTs, then this is where Cubic will do better. In all other regimes, in particular, if the RTT is very small, even at 1 gigabit per second with an RTT of 12 megabits per second, Cubic will make no difference here. So Cubic is the default deployment in Linux, but in practice, for the kind of bit rates we are all using today, for example, in this Zoom session, what we get of Cubic is the Reno part of Cubic. So Reno is really what dictates most of the sharing of bandwidth in the internet today. Okay, and so I'm not showing what utility function Cubic has. That's an interesting work to do. It has not been done as far as I know. So if you're interested, you might write a paper to see what utility function Cubic is reaching in the internet. But let's discuss another topic. This other topic is motivated by the buffer bloat syndrome. What is the buffer bloat syndrome? Well, this is illustrated by this diagram that I borrowed from this paper. BBR is a proposal for a new form of TCP that has received a lot of attention in the past years because it comes from one co-author, Van Jacobson, who is one of the historical authors of TCP Reno. So of course, if this guy invents a new thing, it must be better. But several papers have shown that it doesn't work well, so we won't go through it. Nonetheless, we will go through the motivation of TCP BBR, which we'll see leads to another fix, which is called ECN, explicit congestion notification. Here I'm showing on the x-axis what happens over time when the window increases for a connection that is trying to transfer data through the internet. I'm showing on the x-axis window size, which roughly speaking is proportional to time. On the left y-axis, I'm showing rate, and on the right y-axis, I'm showing the round-trip time here. And the green line is the rate. This is a highly simplified thing, of course. We see that when you open your connection, you try to transfer your many bytes from the other end of the world. Then you start small with slow start and then additive increase, and you increase your rate until you reach the capacity. What capacity do you reach? Well, you don't know. But in this simple model, we could imagine somewhere there is a bottleneck for us. In reality, it's more moving, in particular if your connection is long, things are a moving target. But in this thought experiment, let's assuming it's fixed. So there is a target, a bottleneck capacity, which is a link somewhere in the internet that you're sharing with others. When you reach this capacity, then the rate, the useful rate that you obtain remains the same because this link is fixed. If the others don't move, you will not get more than that, right? In particular, if there are many connections using that link with you, your impact on those others is small, unlike what I showed in the other example where I had only 3 connections. If there's 1,000 connections, of course, when you reach the bottleneck link capacity, you push the other connections a bit down, but this is minimal. This is not shown here. So this is what will happen. First, you increase your rate, then you have a constant rate, which is the bottleneck rate. But what happens to the buffer? Now, if the buffer at this bottleneck link is large, first, what happens to the buffer and the delay? So the delay at the beginning is only the propagation and transmission time. But as you reach the bottleneck capacity, then you're going beyond it. So you reach just a point where you need to buffer things. So you will start buffering data. And as you buffer data, the size of the buffer grows. Therefore, your delay also grows. That's the key point. If you put a buffer somewhere, it's good because the randomness of the traffic will be absorbed by the buffer. If 10 packets want to go out at the same time, 9 only will be able to do it. Only 1 will be able to do it, and 9 will be stored. They will not be lost. They will be buffered, and they will go out a bit later. But if you continue sending, oh, sorry, here I'm assuming on the x-axis, we assume we continue to increase the window size. So if we increase the window size, we increase the rate. But of course, the delivery rate will not increase because the link capacity imposes a certain rate. But we fill the buffer. Right? until we have a loss here. So it's only at point B that we will detect that we went too far here. So what I said here was misleading. We don't detect that we go too far here. We detect it at this point. So there is a delay from A to B where we increase the window without any benefit for our rate, because we don't get more out of this pipe. We get the capacity of the bottleneck here, but with a negative impact, which is a worst round trip time. The delay increases, and if the buffer is very large, the increase can be a very large here. So this is exactly the problem here. We would like to operate here. We would like to be just at the link capacity. We would like to discover this value. And once we have discovered this value, we should not fill the buffer. We should stop sending more, continue sending at the rate that we have discovered here, and stay there. This is what, if we stay there, the buffer will be less full, which means the delay will be, in that case, half. Larger delay means the interactive connections will be better. When you go to a website, the delay is, of course, painful. If you share a whiteboard with Zoom, for example, the delay is impeding your interactivity. So this is the problem. This problem can be solved by a number of ways, attempts like BBR, or one of them is called explicit congestion notification. Well, explicit congestion notification, the idea is that we should be able to signal congestion without dropping packets. In fact, that's a very old idea. It's older than TCP congestion control of the internet. It was present in DECnet. That was putting a DEC bit in the IP or the network layer of DECnet, was putting a bit saying, oh, the network is congested, be careful now. So how is it done? Well, let me illustrate on this animation here. It's done by a combination of the IP header and the TCP header. So those are the obscure fields that we did not discuss in the IP header and the TCP header. When a router feels that it is congested, before dropping packets, instead of dropping packets, what it can do is mark in the IP header, so the IP header is in light gray here. So this packet is sent by the source. This router is congested. How does a router know it's congested? We'll see in a second. Then it marks a bit in the IP header. When this packet is received by the receiver, of course, this doesn't help the receiver. Who should know about this is the source. So we need to give that information back to the source. How can we do it? Well, we have TCP for this if we use TCP for congestion control. So we will echo this mark into the TCP header in a field that is together with the ACKs. And then when the source will receive this, a round trip time later, it will see, oh, this ACK that I'm receiving is marked with a red cross. That means there was congestion. I can interpret that in the same way that I did if it would be a loss. I can do multiplicative decrease. In fact, this is exactly what DECnet was doing in the 80s when the source was receiving the DEC bit, an echo of the DEC bit marked, it would do multiplicative decrease and reducing the window here. So the reality is a bit more complex. So there are multiple bits. There are multiple bits. There are 2 bits for congestion control in the IP header for historical reasons, but any of the 2 bits can be used to mark congestion. But you also need to mark whether a flow should use this system or not, because not all sources are using ECN. Many sources today are using ECN. Many access networks of Swisscom, for example, are using ECN, but not all networks are using ECN. So and not all software in the sources and servers are not all using ECN. So if you're not using ECN, of course, the router should know. This router here, the router here that is congested should know whether this packet should be marked or not. If I am congested and I see a packet that does not follow ECN, then the only mechanism I have to signal to S that it should reduce its rate is to drop the packet. So a router will mark if the flow follows the rules of ECN, otherwise it will drop. Now there were tricks, like in order to avoid cheating, there was some randomness. This is why there are 2 bits instead of, we have 4 possible code points for I'll skip the details now. In the TCP header, we will have an echo, which is called ECN echo, which, as the name duly indicates, is simply echoing the fact that a packet was marked as congested. Now, the echo is repeated until the source indicates that it has reduced the window. So there is another bit that you need to set to indicate that you reduced the window. This is a way to reliably send this bit. In some sense, the echo is 1 bit that we want to send back to the source, but this ACK could be lost. So we want to make sure it is not lost. And also another mechanism is in TCP Reno, when it uses ECN, we try to decrease the window size only once per round trip time. So this mechanism will support this. So this is how things might look like when I look at the congestion window size if I use ECN. There will be no slow start because there will be no packet loss, at least in this optimistic scenario. And we will have only multiplicative decrease and additive increase. By the way, are you able to pattern match those labels to those different phases, 1 and 2? This is our next speak up poll. I close the poll. Zoop. I close the poll in a few seconds. Here we are. And the correct answer is C. So with ECN, things are much nicer. As long as you receive acknowledgements, you increase the window. This is exactly the same as we saw before. When you detect a mark, not a loss, now there is no loss in this TCP connection. When you detect a mark, you apply the multiplicative decrease, then you increase again, etc. So then we have exactly this additive increase, multiplicative decrease, as in the theory of last week. We have it exactly with ECN, which has a lot of nice effects. First, we don't have these ugly slow start and fast recovery heuristics to implement that may have an impact on performance. Also, there is no loss for this TCP connection because, or at least no loss due to congestion, which means that there will be no need to repeat packets, no delay in the socket buffer, in the receive socket buffer. This is what I mentioned awkwardly a few minutes ago. So ECN is supported by a combinations of bits in the IP header and in the TCP header, where the bits in the IP header are used to convey the information whether we support ECN. And as we will see, there are multiple versions that support ECN. There is TCP Reno or Cubic, both in the same way they support ECN. And there's DCTCP that we'll discuss next week that uses ECN in a different way. And there are the bits in the TCP header, which are used as echo bit and also in the reverse direction as a bit to signal, to be an acknowledgement that the echo bit has been received and that the window has been reduced. last question is, how does a router know that it needs to mark a packet? Before we said there is congestion when there is a loss, which means routers are stupid. They have buffers, and whenever the buffer is full, they drop packet, right? And this is called tail drop that exists, and this is what bridges do, in fact. But routers can be a bit smarter, in particular if they use ECN. So they could do things like they could use queuing theory, and there's a number of methods that have been used. So all those methods fall into the keyword of active queue management, but the most widespread method is very simple. It uses this. It computes a smooth estimate of the average queue length. So the instantaneous queue length here is on the x-axis. The idea is that we have a buffer which is large, but we don't want this buffer to be used entirely. So we put a threshold, a maximum threshold. We will still use it if things go wrong, but the target is to not use it. And then when the buffer size is becoming close to the threshold, then we drop packet with a certain probability. And with, in fact, given by this response law, which is a linear function here, when we are at this minimum threshold, we don't drop. That means as long as the average queue size is in this region, there is no packet, let's say drop, no packet marking. When with this region, we mark with a probability that is given by this function here. And when we're above the threshold, we mark all packets. We mark with probability 1. I said the average queue size as similar things done in TCP. This is a exponentially smoothing filter that measures whenever a packet comes, we see how many packets are in the queue. That gives us the measured queue length. Then we smooth that, and this is the input we use for this mechanism here. There are other bells and whistles that I will discuss. They're not discuss, but this is what red does here. So with red, we have a mechanism that will have the effect that as long we will, as much as possible, operate in this region here. When the queue starts becoming fuller, then we will start giving feedback. And if everything goes well, we will never go in that region, at least not for large periods of time. So we will have the best of both worlds. We have a buffer that can occasionally use to avoid dropping packets, but will avoid the buffer bloat syndrome. The buffer size will remain small most of the time. Voila, that's all for today, folks. Take care and have a good continuation.